Solve one problem on unidirectional steady-state conduction heat flow through slab of varying cross-sectional area, that is uniformly tapered rod of square cross-section. We will read what is the given question. Heat is conducted through a uniformly tapered rod of square cross-section and length 40 cm. The temperature at one end is 500 degrees Celsius and the side of face is 2 cm. At the other end, the temperature is 100 degrees Celsius and the side of face is 7 cm. The conductivity of material is 52 watt per meter Kelvin. Assume that the heat is conducted only along the length of the rod. Find first the rate of heat conduction, second temperature at point 20 cm from the hot end.
This is the example of slab of varying cross-sectional area. Let us first construct the diagram as per given data. Here the uniformly tapered rod of square cross-section is given, whose one end is at 500 degrees Celsius and side is given 2 cm. Now its a total length is 40 cm and other end is at 100 degrees Celsius and the side of the square cross section is given 7 cm. Now we have to find out rate of heat conduction, that is Q, and temperature at 20 cm from hot end. That is, here is the 500 degrees Celsius. So here is the hot end, and from this hot end at a distance of 20 cm. That is, we can say if we observe here total distance is 40 cm. So distance 20 cm, that means at the center we have to find out what is the temperature. Now we will construct here one side, that is one cross section at a distance x. So we will draw here one side, that is for the square cross section. We will say this one side is having length Lx. Why Lx? Because this cross section is at a distance x from this hot end. So I will show here. So here is the distance x. Now we have to find out what is this length Lx. Now from this diagram we will take one ratio. Now this ratio, we will take this difference in side from this. So this is the first side, I will give here suffix 1. This is the second side, I will give here suffix 2. And here this is the side at a distance x. So we will give here the suffix x. So difference in side, that is difference in this second side, that is L2. So this side is known as L2, this side is known as L1. So L2 minus L1 divided by Lx minus L1. So L2 minus L1 is equal to 40 cm. So we will write 40 divided by Lx minus L1, that is x. So we will write here this relation, that is L2 minus L1 divided by Lx minus L1, which is equal to this 40 cm we will consider here as a L. So L divided by x. Now we will put all the known values. So this L1, L2 given in centimeter, but we will convert it into meter. And this L is also given in centimeter, we will convert this into meter. So 0.07 minus 0.02 divided by Lx minus 0.02, which is equal to 0.4 divided by x. Now here two terms are unknown, that is Lx and Lx. So we will find out the value of Lx. So by cross multiplying here 0.4 Lx minus 0.008, which is equal to 0.05x. So Lx is equal to 0.125x plus 0.02. So this is the one side for this square cross section area. Now what is the area for this square cross section? So we know that the area for the square is, it's a side square. So we have to take the square for this Lx. So area normal to heat flow, that is A is equal to Lx square. So Lx, that means this bracket. So we will take here this bracket square. For this uniformly tapered rod, conduction process is taking place. So we will apply here the Fourier's equation. So what is this Fourier's equation? That is q by a is equal to minus k dt by dx. Now we will put here the value of a in terms of x, 0.125x plus 0.02 square. Now at the same time we will transfer this dx to the left hand side. So this is the new equation, q dx divided by 0.125x plus 0.02 square, which is equal to minus k dt. Now if we observe this equation, how many variables are there? So these variables we can define from this diagram. So here this is a question for varying cross sectional area. That means if we observe here the parameter x, that is variable, because if we observe here as the length is getting varied, then this temperature is also variable. So from this equation we come to know that x is variable as well as temperature is also variable. We also come to know that here q, so q is not the function of x. So this q we have to take the outside, and here thermal conductivity k, that is also not variable. So only two terms are variable, that is this equation at the denominator, which is the made up of variable x, and here is the temperature dt, that is also variable. Now we will put the boundary conditions. So if we observe the diagram here at this first end, what is the distance x? So here at the first end x is equal to 0, and when x is equal to 0, temperature T is equal to T1, because for this first end we have given here suffix 1. And in the same way at the other end here x is equal to L, because this total length is L. When x is equal to L, then temperature T is equal to T2. Now we will apply the boundary conditions and we will take the integration on both sides. So we will take here q outside. Now integration of dx divided by 0.125x plus 0.02 square, which is equal to minus k integration of this dt. Now for this integration, if we observe here is the variable x, that is dx is there, and for this area also here this is also the variable that is made up of x, and q is not the function of x, so we have to take here the outside. Now for this x, limit is from 0 to L, so we have to give here limit from 0 to L. Now in the same way on the other side, k is not the function of t, so we have to take this outside, and for this dt we have to give the limits, that is from temperature T1 to T2. So here we have to give this. Now if we observe here area A, we will put the value. So q integration of 0 to L dx divided by 0.125x plus 0.02 bracket square, which is equal to minus k integration of T1 to T2 dt. Now we will solve this integration. So if we observe here, this is the form of integration of 1 upon x square dx. So what is the answer for this integration? So whenever there is 1 upon x square, so its answer is minus 1 by x. And for this denominator here again there is one term, that is 0.125. This is the coefficient of variable x, so again we have to rewrite this. So this term is in the denominator, so we have to write this term in the denominator, that is multiplied by 0.125. So now this minus 1 by x, we have to write this. So we will write minus, whenever there is x square is there, so this whole term we will consider as a x square. So we have to write as a solution minus 1 divided by this whole term, that is 0.125x plus 0.02, and again we have to multiply here with coefficient of x, that is it is in the denominator, so it is 1 divided by 0.125. Now we will give limits here. So what are the limits? That is from 0 to L. Now here integration of dt, so integration of dt, that is t, and here we will give limits, that is t1 to t2, and we have to write the constants as it is. Now again we will solve this. So these constants we have to write as it is outside the bracket. Now for this bracket here are 0 to L. So instead of variable x we have to put here L. So what is The answer minus 1 divided by 0.125L plus 0.02. Minus, we have to give here the second limit, that is here minus 1 divided by, now this if I put x is equal to 0, this whole term will become 0. So minus 1 divided by 0.02, which is equal to, now if we observe minus k t2 minus t1, because this is the variable t, so we have to put here limits, that is t2 minus t1. But minus sign is there, so if I multiply with the minus sign inside, then it will become k t1 minus t2. Now again we will simplify this, so here minus minus will become plus and here it will remain minus. Now we have to find out the rate of heat flow Q. So only one unknown term is there, Q. We have to shift all the terms to the right hand side. So here this k into t1 minus t2 multiplied by this 0.125 divided by, we have to transfer this whole bracket to the denominator. So here this plus 1 divided by 0.02 minus 1 divided by, we have to take this as it is. Now we will put the value. So what is the value of T1? That is 500 degrees Celsius, T2 100, then K it is 52, that is also given in the question, and L, so what is the length? L 40 centimeter, that is 0.4 meter. So when we put all the unknown factors, then we will get the answer of Q, that is 72.8 watt, and this is the answer of first question. Now we will find out the temperature at the distance of 20 centimeter from this hot end. So we will consider this x, that is distance x is equal to 20 centimeter and that is equal to 0.2 meter. So what is the temperature at a distance x? So we will consider this temperature as a Tx and we have to find out this temperature Tx. Now if we observe the formula for Q is equal to 0.125 T1 minus T2K divided by 1 divided by 0.02 minus 1 divided by 0.125 L plus 0.02. Now here there are two variables, that is T1 and T2, that is at the first end and at this other end, and in the same way the length is also included, that is this total length, and this L is at the other end. So how many parameters are there for this other end? That is this T2 as well as this L. Now instead of T2 and instead of L, if we put this temperature at a distance x, and for this horizontal distance L, we will put here the distance x. So we will put here, that means we can say we will replace these two parameters. Instead of this suffix 2, we will take here for this suffix x. So here is the new equation, that is 0.125. Now T1 is 500. So 500 minus Tx, K is 52 divided by 1 into 0.02 minus, now here 0.125 into x. So what is this x? X is 0.2 meter. So we will replace here as a 0.2. So 0.125 into 0.2 plus 0.02. So what is the temperature Tx? Now here Q is known. So we will put here only one unknown term is there, that is Tx. So Tx is 188.88 degrees Celsius.